number, that means n is a variable, that must be a natural number, then n is either even or odd. How do I express it? I can express it natural n, if n is a natural number, that then even n or odd n. All right. Now, even n and odd n, any one of them will be true. So, in that way you can see, just let us once again look at the last example here, that looks like a complicated sentence, but as soon as we write in the form of predicate logic, and if we understand that, then it becomes really succinct. Okay. Now, we have said that predicate logic requires variables, I mean it allows you to have variables, and in addition to variables there is another thing that predicate logic has introduced, and that is called quantifiers. Now, there are two basic quantifiers in first order logic or predicate logic. For all, which is denoted as this V with a horizontal line across it. Now, for all, this is also known as universal quantifier. For example, if we say for all x, then that is I am talking of all, for any value that x can take, the proposition will be true. Another one is there exists, which is meaning which is also called existential quantifier, that something is existing. Okay. There is a subtle difference again between these two. So, for all x, suppose think of a set, let us just think of a set. All right. Let us try to do this. Suppose I have got a set, and in that set I have got a number of elements. All right. Now, when I write for all x, something is true, I write p x. That is that p x, I just say that p x is true for all x. Now, just I mean these are not, this need not be denoted as x's, I can just put thick dots here, this has got nothing to do with, these are just elements of this set. When I write this, then what I mean is that this p x will be true for any element that I choose from this set. All right. Now, suppose let me choose another color here, and I am marking some, or might be this is not very visible. Let me take this color, I mark them with this. There are some special elements, and I write, suppose I write there exists x such that q x. All right. That means this q x should be true. There should be at least one element in this set for which q x is true. Now, here I have shown that for these two elements q x is true. All right. Let me just write down an example. There exists x such that holiday x. Okay. Now, if 1, 2, 3, 4, 5, 6, let me put in another one. Suppose these are the 7 days in a week. Now, is this statement true? There must be an element in this set. Suppose this is the days of the week. Now, obviously, here lies Saturday and Sunday, 2 days for which holiday x is true. Therefore, there exists an x, there exists a day for which holiday x is true. At least one would have sufficed. Suppose Saturday is not a holiday, okay? Only Sunday is a holiday. So, this one is not a holiday, this is just an ordinary dot, but at least I have got one, then this statement will be true. This entire predicate will be true only if this entire thing, I mean if there is at least one x. On the other hand, in order that this statement is true, all these elements in this set must satisfy P x. That is the basic difference. All right. I don't know what is happening. So that is the essential difference between existential quantifier and universal quantifier. Now, let us look at some more universal quantifiers. All dogs are faithful. Now, I write that x is faithful is being denoted as faithful x, x is a dog is being denoted by dog x. So, I can write for all x, for all dog in that set, for all dog, dog x implies faithful x, and that is true for any x, which will make dog x true. That means, for any dog, any x, that is for any x that is a dog, this faithful x will be true. Now, how can we do this? The next statement, all birds cannot fly. Suppose we decide that with fly x will denote x can fly, and x is a bird is denoted by bird x. All birds cannot fly. Therefore, it is not the case that for all x, bird x implies fly x. Forget about this not part right now, forget about this. In that case, if I had written this, for all x, if x is a bird, then x can fly. Now, that is not true. I am saying all birds cannot fly. So, this statement is not, this entire statement for all x bird x implies fly x is not true. So, this is the implication, this is the expression for this statement, predicate logic expression with quantifier and variable for this statement, all birds cannot fly. Now, let us quickly revisit the quiz that we had done, and I said that I played a little trick, I did a little bit of adjustment. The statements which were given were mammals drink milk, man is mortal, man is a mammal, Tom is a man, these were given, and I had written them as mammal Tom implies drink Tom milk, like that. But this statement is unfortunately not a statement made for Tom alone. So, I should write it in a little different way. How should I write it? I can write it in this way now. Now, I know predicate calculus. So, why should I do that sort of adjustment that I did? So, I can write for all x, mammal x implies drink x milk. Note here, milk is a constant object. Among all the food, milk is 1. X is a variable. So, for all x, mammal x, if x is a mammal, I take one animal and see whether that is a mammal. If that is the case, then x will drink milk. Man is mortal. For all x, if x is a man, then it is mortal x. Man is a mammal. Here I should write, I should write for all x here. Here I should have written for all x. So, I should select here I should have written for all x with some color. All right, this was a mistake here. So, it should be for all x, man x, mammal x, and Tom is a man is Tom is a man was as before man Tom, there was no problem with that at all. So, now you see we can do it in a much easier way, much more natural way instead of making adjustments, and that is the power that predicate logic has given us. Okay. Now, let us look a little bit, those examples I could have done, these examples right now,